Yes.
Jeremy.
Hello.
Can you hear us?
I can hear you. I'm hoping you can hear me before I.
Yeah, please go ahead.
Great.
Thank
Perfect.
you.
All right, then I'll go ahead and share my screen and get started. Start from here. So make sure that's coming through. Not yet. I think you looks like you're just getting my camera right now. There we go. So I am glad to be invited here to talk for a little bit about grayscale lithography on the MLA 150.
Jeremy, you're not in
Yes.
presenter mode.
Oh, yeah, that's fine. Let's pull that up. Just get the full screen. So a little bit of context, first of all. I'm a staff scientist at Lawrence Livermore National Laboratory in California in the implantable microsystems group, where we do microfabrication of implantable medical devices, mostly for brain recording and stimulation. And my personal background is actually mostly in neuroscience and some biomedical engineering. So MEMS and microfab is not, I'm not as big of an expert in the area as many others, probably as many of the people in this room. So this is actually very much a baseline intro level discussion of what is grayscale, why I might be interested in it, and how do we do it as kind of a tutorial at a tutorial level on the MLA 150 as a tool. Another thing that is relevant for context here is the clean room at LLNL and the implantable microsystems group. We're very much a experimentation and prototyping kind of facility and not a production facility. So that affects the kinds of things that we're working on. We do a lot of unusual procedures and design new process flows and a lot less large-scale fabrication. So what is grayscale lithography for folks who aren't really familiar? We just saw a bunch of really impressive final results of the things you can do with really high-end grayscale. But for anyone who needs a really baseline introduction, regular lithography, obviously, everything is either exposed or not exposed. This is black and white lithography, as opposed to grayscale lithography, in which different quantities of light dose result in different heights in the resist across different points. Easy to scan, get complex patterns over the entire wafer, again, like you were just seeing. This is, of course, with a positive photoresist. So the process by which this happens is based on, you've got the exposure curve and absorption curve for photoresist here in the upper right corner. I don't think you can see my mouse, that's fine though. Basically, photoresist obviously is absorbing the light so as to become exposed and then clear away with the subsequent developer. But that process also renders it transparent to the wavelength of light that it is otherwise absorbing. So as photoresist is exposed, it is exposed from the top down gradually, which means that if you only expose it part way, only some of it develops off when you go through your develop steps, and you end up with your grayscale 3D pattern with different heights as a result. You can actually do this with negative photoresists too. That's been explored in some places. It's not something I've done. But because polymerization happens from the top down in negative photoresists, when you clear off the remaining resist, you just lift off all of your patterns. So if you want to actually attach something to a substrate, some people have worked with a transparent substrate writing from below. I think this has been done with SU8, among other things. I'm not sure that would be very easy to do in the MLA 150, but it's an interesting alternative process. So the kind of things that we're producing, this is just a quick look. We're making these implantable, basically sharp little spikes that are part of our surgical process. And so you go from, you've got a design. I've been using K-layout for my designs, and I'm going to actually switch over to share screen to show a little bit of K-layout later, although I won't go into too much detail. And then that gets converted into resist. And then I have some post-processing steps that I'll comment on for transferring a 3D pattern in resist into a 3D pattern in silicon or other substrate materials. But for starters, parameters with grayscale. The MLA 150 runs from 0 to 510 millijoules per square centimeter in steps of 2 millijoules per square centimeter when doing grayscale. I did my grayscale processes with AZ4620, spun to 5 microns. This is not a grayscale photoresist. There are dedicated grayscale photoresists, like I list a couple down there, MRDWL, MAP1200. These are intended for grayscale. They are optimized for it. They can be spun on, I believe, very thick and then allow for high detail patterns. But I was using 4620 because the principles of grayscale actually will run for most resists, and it worked quite well for my process needs without having to bring new chemicals into our facility. Using 4620, I saw grayscale responses, basically steps between 40 and 200. Below 40 millijoules per square centimeter, there's no response in the resist. Above 200, it's fully cleared. I was doing this with the 405 nanometer wavelength laser in the MLA 150, very linear, and this gave step heights in the resist of about 60 nanometers. You can get very, very precise vertical heights with grayscale. Again, like, this is not a example of grayscale at its finest. This is a very experimental kind of put together procedure, and I'm still getting a 60 nanometer resolution in our heights. There's two things for those of you who are particularly eagle-eyed here. There are two things wrong with everything that I just said. First off, 75 steps. You would actually fit 80 in that 40 to 200. Whoop. Let you settle that out first. There we go. So one thing that I've found as a potential challenge with grayscale work, depending on what your actual intended application is, when you have exposed near down to the bottom, it can be challenging to get, 60 nanometer levels of precision and less on the bottommost step of a grayscale development process. Because, at that point, any variation in your photoresist thickness from the spin-on is going to be coming into play. And any minor variations in the way the developer is swirling how much of your, wafer has a pattern on it versus not is going to affect these development rates just enough. That's why back here on this previous slide, you can see at the point of the tip of this device, there's a little bit of kind of roughness and a little edge that's kind of sticking out. Might require some post-processing if you have a process where you have to do grayscale lithography all the way down to the substrate. So that's something to keep in mind that might be worth paying attention to when developing processes for this. I also was using the 405 nanometer wavelength laser, even though 375 is more optimal for 4620 photoresist. But different wavelengths, different optimal amounts means you're going to expose the dose that the photoresist receives is going to be affected. So by using a less than optimal wavelength, especially because I was doing this not on a well-established process with an established grayscale resist, meant that I was able to get less of a impact on the resist per unit of energy delivered, which allowed for slightly more precise steps. So if you're doing grayscale, you're going to have to pay attention to the actual exposure curve. How much of a dose is going to get you how much height in your final resist. To some extent, there's tons of material out there to look this up. To some extent, maybe you'll want to test it on your own devices and your own patterns, especially because this can be affected by development times and things like that. This is from a paper which is out there. This is a standard eye-line resist, and it's using a grayscale mask as opposed to direct writing. But you can see it's very linear. This was a plot that I put together when I was doing this work myself out of a very small amount of data. Again, pretty linear. You can see there's a little bit of a curve in here. But basically, the way that I approached this, because I wanted to get a really hands-on understanding of all of these values for myself from the beginning and kind of top down, I put together these test designs, ran them, and measured every dose that was capable of being delivered by the MLA 150. It has, I I measured 128 steps. It can do up to 256, but with the photoresist I was using, the upper half of that was already fully developed. So I'm going to switch over real fast to K-layout. There's plenty of tools that can be used for this kind of process for layout here. I used K-layout, but really I think anything that can export a DXF file is probably going to suffice. This is one of my early test wafers for determining how the Grayscale was working in the MLA 150 and in our tool set. And it's really a pretty straightforward process. I just put together these 128 little squares and then measured after developing what the resist height was in each one. And these were set to 1, 2, 3 numbered layers in K-layout. So basically I ended up with, this is exposed at 2 millijoules per square centimeter, this one at 4, the next one at 6, the next one at 8, and so on. And then could see, where does my dose response start, where does it stop, record all that, and take down that plot that you saw earlier of exactly what heights I got from what wavelengths, and then I could do my designs from there. I also have some more precise designs in here, including the actual final layout for the kind of stiffeners that we were producing, looking at staircases, other things like this. K-layout's like any other one of these layout softwares. I'm not going to try and give you a tutorial in it because, frankly, a lot of you probably have much more experience doing these kind of designs than I do. But it works well for this process, including for Grayscale, and it has built-in API macro development functionality, so you can use Ruby code to do very complex things. I put together at one point the most ramshackle pipeline you've ever seen just for some testing that converted an STL file into a Grayscale DXF, and it technically worked. So you can do all kinds of things if you're willing to dig into this kind of coding backside of it. As far as actually doing this on the tool set, as a bit of a tutorial how-to side, it's really very simple. So you've got the layers here on the right. The layers are just numbered 1 through whatever, and so I can export this file with layer 1, layer 2, layer 3, up to, you know, layer 100 and layer 108, layer 150, and I just save this as a DXF file, and then I can bring that DXF file straight to the MLA 150 and load it in as a Grayscale pattern. So what does that process look like? Again, kind of at the tutorial level rather than any in-depth scientific side. The MLA 150, you convert a new design here on the design page. It pulls up its conversion process. You can select file type DXF Grayscale. It also runs bitmap files. I personally had problems when I tried to do this with bitmap because of enormous file sizes. Grayscale files can run extremely large once they get converted for use on a tool, so that's something that you might want to be aware of when troubleshooting this kind of process. The DXF Grayscale files were still very large, but not so large that the process wouldn't run. K-layout, the K-layout file loaded here into the MLA 150 software automatically converts layers 1 through whatever, 1 through 100, to gray values 1 through 100. So we've immediately got our conversion process. It can also upload gray tables. You can prepare a whole gray table in advance, name your files differently. This is also the stage of conversion where you would address overlap if you make multiple layers that overlap one another. But if you avoid that, you just don't have to bother with it at the software end. This is then you accept this, go into the final page, high quality, fast, mode choices for the MLA 150. This is all conventional, the conventional process for running something on the tool. One thing to keep in mind, if you're used to running stuff on the MLA 150 and you're trying Grayscale for the first time, it can be pretty slow. This is not a dedicated Grayscale tool. Heidelberg does produce other specifically Grayscale tools. You just heard about a bunch of specific Grayscale tools from Wraith. So this can take a fair bit of time. Pattern conversion for a production facility isn't a time constraint because you're going to do it once and then run the same thing a million times. but it can take maybe 20 minutes, which is different from regular patterns. So just be aware if it's taking a very long time, it might just be working, not necessarily hung. I found that exposing a full 4-inch wafer on the MLA 150 would take a couple of hours, even with the expose mode set to fast as opposed to high quality. So that may be a throughput concern if you're trying to do grayscale in a large-scale production facility. For experimentation, that wasn't too big of a problem for me. So what do we do with all this grayscale? You saw some examples of final devices, and there was some mention of it just in passing in that last talk, stuff about Fresnel lenses, various other lens patterning. In fact, I think these visuals might be from one of the same sources that you were just seeing. So some people have developed mold approaches using Ormocomp and Ormo stamps to produce structures derived from the photoresist pattern. In my case, I was exploring a transfer etch approach. So I used a DRIE process after the grayscale resist to transfer the pattern from the photoresist into a silicon substrate. So basically, I developed a DRIE etch recipe. May have lost screen share. I developed a DRIE etch recipe that could etch both resist and silicon, and then was able to run that such that the pattern present in the resist would be transferred as is into the silicon substrate. And this should be possible for any substrate material that you can develop an etch recipe for, capable of etching both whatever your grayscale resist is and whatever your substrate is. In our case, this was for making those silicon stiffeners that I was describing before that we attach to our medical implantable devices. If anyone has questions about that, I can talk about it in a little more detail, but that's what I've been doing with this process, is doing this transfer etch. Yeah, so there's various applications. Fresnel lenses, diffractive optical elements. People do combined refractive and diffractive optical structures because grayscale allows you to do such complex patterns across an entire wafer. All kinds of shaped MEMS, actuators, turbines, micro engines. A lot of people use grayscale for microfluidics because you can design, whatever your full pathway is and then print it all at once in a single grayscale pattern step. Yeah, so like I said, very surface level introduction, but just wanted to give a quick overview of my experiences and what my process is for doing this kind of grayscale development with the MLA 150 in particular as a tool. I have to give thanks, obviously, to various folks from the L&L clean room and other people in the implantable microsystems group who helped me put a lot of this together.